Hello students, so in this lecture we will be discussing about super paramagnetism. Now, uh, if you if we discuss if we look into the different types of magnetic materials available, the most common is the ferromagnetic materials, that is iron, nickel, cobalt, transition metals, uh, where in ferromagnetic materials this magnetization M, which is actually the sum of the small magnetic dipole alignment. They are aligned in such a way that the susceptibility, that means M is equal to chi H, the susceptibility is close to 1. That means all the magnetic dipoles, they align along the direction of the magnetic field when the magnetic field is applied. This is the property of a ferromagnet. It means again, if you have an antiferromagnet, the magnetic dipoles will align in the opposite direction. If you have something called a paramagnet, then the magnetic dipoles will not preferably align in the direction of H, but the tendency may be to align in this direction. So this value is positive, but is much less than 1. Now, however, if we go to the nano scale, this paramagnetic property is exhibited by some other type of materials where the magnetization, this I mean the magnetic dipole direction, they automatically they flip their direction. That means if they were in this direction, they will automatically flip the direction towards the opposite side. And this is what will happen even if the material is a ferromagnet. Or it can also happen in other type of materials, like if the material is say another type of called ferrimagnet. Ferrimagnet. A ferrimagnet is such a material where, although the magnetic dipoles are aligned in the same direction as the applied magnetic field, as in the case of a ferromagnet, however, the magnetic dipole strength is all the magnetic dipoles are not of equal strength. Some magnetic dipoles will be of higher strength, some will be of comparatively lower strength. So this type of material is called a ferrimagnet. So this property of superparamagnetism, which involves flipping of the magnetization direction, occurs in ferromagnets and ferrimagnets. And it is not only you need to go to the nanoscale, but you need to apply a certain temperature which is low, and that temperature is actually the time taken by two slips. For example, if you have a magnetization direction in this direction and it flips in this direction, so there is a certain time which is required to cause this sort of operation. That time is called Néel relaxation time. Néel relaxation time. Néel relaxation time. Now, In the absence of a magnetic field, when H has not been applied, this magnetic field is zero. The time used to measure the magnetization of the nanoparticle is much longer than the relaxation time. So the time taken to measure the magnetization is it's much longer than this Néel relaxation time. And at the Néel relaxation time, what happens is that what is being observed is that usually if you look into this paramagnetic plot, so if we have this image plots of different materials, so say you have magnetization versus magnetic field. So this is how a ferromagnetic material will look like. Cobalt, nickel, iron, which are the common ferromagnetic material. So you have a coercivity, you have a retentivity. Okay. Now, if the material is a paramagnetic material, the magnetization will be, there won't be any width. Okay, it will be like this. It will be like this. However, if it is a super paramagnetic material, the shape of the plot will be like a paramagnetic one, but the only thing is that the saturation magnetization will be much larger. This value, ms saturation magnetization, will be much larger in case of a super paramagnetic material. That is why these average magnetization, since they flip so fast, the magnetic lines of force, I mean the sorry not lines of force, the magnetic dipoles, they flip so fast that the average magnetization, there is no still there is no coercivity which can be seen in case of a supermagnetic material. Now, in the state when the material is in supermagnetic, the external magnetic field is able to magnetize the nanoparticle similar to the paramagnet. Okay, so that is why you have a plot like this, which is similar to a paramagnet, but it is of much higher dimension. This ms, the saturation magnetization value, is much higher in the case of a super paramagnets. Okay. So if the saturation value is much higher, we can say that the magnetic susceptibility of super paramagnet is also much higher than that of a paramagnetic material. Okay. Now let's talk about electron spin to some extent. Now, this magnetic electron spin is nowadays used in a totally different field of study called spintronics. Sorry. Let's take this one. Spintronics. So, spintronics. Spintronics, like electronics, which is based upon the mechanism, the movement of electrons, how the electrons behave in different conditions. Spintronics is based upon the spin of the electron. Now, to know the spin is actually what is a spin? It's basically an angular momentum. So we have orbital angular momentum. Just 1 second. When if this is the nucleus, if this is the nucleus, the electron is revolving around it in a elliptical path, and it is also revolving around it. So this revolution around the nucleus will give rise to the angular momentum, and the revolution along the spin, this will give rise to spin angular momentum. So the both they combine to form the total angular momentum. Now the spin can rotate in either a clockwise or in anti-clockwise. So it can rotate in this direction like this, or it can rotate in this direction. So by right hand thumb rule, if it rotates in this direction, the momentum or the spin momentum will be in the above side, in the top side, towards the y-axis. If we take this as the y-axis, and if it rotates in the opposite side, this ms value will be equal negative, but it will be down. So now this spin value is taken as half, and this is as minus half. The one that is moving up is called half. So these are the two possible orientations of electron spin: plus half and minus half. Now, different electron energy in case of parallel or antiparallel spin in the field. So, the spin E will be responsible for the different electron energies. Like the parallel one will have a different electron energy than negative one. And the directional motion of electrons circulates electric charge. Direction and coherent motion of electrons will circulate spin current. So we will have something called a spin current due to the directional and coherent motion of electron spin. So there will be a spin current a spin current due to the directional and the spin motion. Now the advantage of spin, just for the sake of understanding, the advantage of spin with the case is there are two possible orientations, so it has relatively a longer lifetime, and the combining logic and storage functionalities in spin, there will be a non-volatile energy storage, and quantum computing is based upon this electron spin. And and it will be based upon something called qubits or quantum bits.